A very good morning and warm welcome to one and all. So today we will understand the need of theories of elastic failure and the concept of theories of elastic failure. So basically to understand this, first of all, we have already performed a simple tension test on the UTM machine, right? So basically a specimen was subjected to axial tensile force, means we applied a load and the stress was created and the elongation also takes place, means strain is also produced. Now the next step is we plot the result, that is the result of tension test are expressed by means of stress strain relationship and plotted in the form of the graph. So as far as this graph is concerned, we get at different points P as a proportional limit, the stress is directly proportional to strain, E is nothing but elastic limit, Y is nothing but the upper and lower yielding point, U ultimate tensile stress point, and F is the failure point. So let us consider that the stress corresponding to Y1, that is a yield point, is nothing but the SYT, okay, which is nothing but the yield strain, and the stress corresponding to point U is nothing but the SUT, which is nothing but the ultimate tensile strain. Okay. Now let us consider, for example, that for a specific material of which the specimen was made, the SYT is 300 megapascal and SUT is 500 megapascals. Okay. So basically what happens when we apply an axial load or a stress on a material, and if the value exceeds 300 megapascal, that is the SYT is greater than 300 megapascal, means what? There is a permanent deformation in the material. And if the axial stress value is more than the 500 megapascals, that is SUT is equal to 500 megapascals, the corresponding component will break, right? So basically, now whatever we have studied or whatever the graph you have got, the corresponding loading condition was a uniaxial loading. So that is the above scenario was only for a uniaxial loading condition. So uniaxial loading condition means what? If you look into this figure, if this is a mechanical component, it is subjected to the tensile load, that is a sigma x in uniaxial direction, that is only in one direction, right? But basically what happens when we apply the stress in all three directions or two directions, that is in practical cases there is a biaxial or triaxial stresses acting on a component, that is the component is subjected to the combined loading. That means what? In this case the component is the stress is acting in maybe in all the three directions, that is sigma x or y or z direction, as you can see into this figure. So in such case, when will the component fail? Okay, because the method of tension test, that is a simple tension test we have developed, is considered or is only for a uniaxial stress. Okay, but there are many machine components which are subjected to several loads simultaneously, or you can say the loading condition is a combined loading condition and the stresses induced are a combined stresses. For example, power screws are subjected to torsional moments and axial force. Overhang crank is subjected to the combined bending and torsional moments. Bracket bolts are subjected to the shear and tensile loads. Even if you take an example of a transmission shaft, it is subjected to the combined bending as well as the torsional moments. So the stresses produced in the transmission shaft will be torsional shear stresses as well as the bending shear stresses. So in such practical applications, the state of stresses are complex. Okay, state of stresses are complex means what? The loading is a combined loading and the stress is acting in all the directions, let us say in all the three directions x, y and z. So in such case, when will the failure occur in the component? To know this, we have developed a theories of failure. So different theories of failures have been developed. Some theory will relate the principal stresses, some theory will relate the maximum shear stresses, or some theories will relate the distortion energy stresses. Okay, so basically, first of all, let us understand what are the failure cases. Okay, what exactly is failure? Now basically, now at this particular point we have understand that the theories of failure is basically useful for the combined loading. Okay, but let us understand what is failure first of all. Now if components breaks completely, means it's a failure, is not true in engineering, right? There are three cases of the failure. For example, if the component is actually broken, means the stress value exceeds the ultimate tensile stress. This is the first case. There is a permanent deformation in the object. Means what? The stress value of stress is more than the yield stress, right? The stress exceeds the yield stress. And the third case is there is a value normally there is a value given in the many of the numericals or the practical conditions about the maximum allowable stress, which is denoted by the sigma max. Now already we have understand what do you mean by the allowable stress. Now allowable stress is used to calculate the dimensions of the component. Now basically let us say that you are designing some component, and if you are designing some component and the corresponding equivalent stress in your design is more than the sigma max or more than the allowable stress, then you can say that the component fails. Now in this case the component is neither broken nor deformed, but you have considered it as a failure because your equivalent stress is more than the allowable stress. Okay. Now basically we know that the sigma max or allowable stress is calculated on the basis of SYT upon f of s or SUT upon f of s, depending upon the ductile or brittle material. Okay. So now basically all the complex states of stresses. Now what do you mean by the complex states of stresses? Combined loading means what? Complex states of stresses is a state where on some point stress is acting on or in all three directions, and again there are all types of stresses are originated, like tensile stresses, compressive stresses, shear loads, bending moment, torsional moment, etc. Whatever may be the situation, all the complex states of stresses can be expressed in the terms called as a three principal stresses, which is nothing but a sigma 1, sigma 2 and sigma 3. Now already we have studied into the strength of material about the principal stresses, and in the last video also I have given you the explanation about principal stresses and Mohr circus construction as well as the formula associated with it. Now basically what is principal stresses? First of all, let us understand what is a principal plane. Now principal plane is a plane where the value of shear stress is 0, or you can say the plane where the value of shear stress tau is 0 is called as a principal plane, and the value of normal stresses like sigma x, sigma y, sigma z on that corresponding plane is nothing but a principal stress. Okay. Now this value may be either maximum or it can be either minimum. That is, the value of principal stresses may be either maximum or may be either minimum considering the sign. So sign means what? A compressive we are considering a negative and tensile stresses we are considering a positive. For example, if 50 is a value and 50 and minus 100 are nothing but two values, then minus 100 is the minimum and 50 is nothing but the maximum value. So if you plot on x-axis, if you plot the sigma 1, and on y-axis if you plot the sigma 2, okay. So on the left side of the sigma 2 axis, that is the y-axis, you will get a minus 100 value, and on the right side you will get a 50 value, so which is nothing but a maximum and the minimum value. Okay. Now generally sigma 1 is always considered greater than sigma 2, greater than sigma 3. So basically this condition is for the three-dimensional stresses where the stresses are acting in all the three directions. But again there is a state called as a two-dimensional stresses where we have only two principal stresses, sigma 1 and sigma 2, one is maximum and one is minimum, and the third principal stresses sigma 3 is 0, right. Now see, I am not saying that there is no third principal stress. The third principal stress sigma 3 is present, but its magnitude is 0. That is why for two-dimensional stresses it becomes sigma 3 is equal to 0, and we have only two stresses, sigma 1, sigma 2. Now to understand the theories of failure, already I have created a base, I have given you an introduction. Now let us understand about the theories of failure. Now basically theories of failure is used for a combined loading, so that already I have explained you, right. Now basically what happens if you look into this figure, okay. Now let us consider this as a mechanical component which is subjected to the combined loading. Let us say sigma x in a tensile direction, sigma y in y direction, sigma y tensile in y direction, okay, and again tau xy and tau yx, these are nothing but a shear stress acting on this particular component. Now the loading is a combined loading, and the stresses induced will be the combination of shear and normal stresses, that is a combined loading. So the corresponding stresses will be the combined stresses. So now what exactly we do in the concept of theories of failure, okay. So basically what happens, we are performing a simple tension test, right? From the simple uniaxial tension test, we are getting a different values like SYT, SUT. Okay, so SYT is nothing but a yield stress, SUT is nothing but the ultimate tensile stress, right? So these all the values, whatever the so basically see basically what we are doing whenever you are performing a tension test, right? Okay, from this experimental tension test, you are obtaining a mechanical properties. Means what? The mechanical properties are obtained from the simple tension test, which includes yield strength, that is a SYT, ultimate tensile strength, SUT, and a percentage elongation. Okay, and the space in the tension stress, as I have already explained, the specimen is axially loaded in a uniaxial direction. Okay, it is not subjected to either bending moment or either torsional moment or either combination of load. It's a pure uniaxial load, right? So this is what we are doing, right? And then again, we are considering a practical case of combined loading of a same material, and then with the help of a principal stresses and the Morse circle, we are obtaining the values of sigma 1 and sigma 2, that is the principal stresses, and then we are comparing these results with the above values, that is the SYT and ECUT, the results or the values obtained from the uniaxial tension test. Okay, and then finally we are analyzing the safe condition and we are drawing a region of safety. So I will explain you later on what is how do we exactly draw, how do we draw the region of safety, right? So now basically the one question may arise in your mind that already we have studied a Morse circle construction method for the biaxial stresses where we can find the value of sigma 1 and sigma 2 as well as the tau max, that is the maximum shear stress. Then what is the need for this region of safety, or what is the need of this theories of elastic failure? Okay, so basically you should understand that we only get the magnitude of the stresses, we get the value of the stresses from the Morse circle. For example, this is a Morse circle construction which I have already explained. Here we have already obtained the relationship for the sigma 1, sigma 2 and tau max. Okay, so we have this Morse circle represents the stresses and we can calculate the values of sigma 1, sigma 2, tau max accordingly. Okay, but we don't understand or we don't get the information about the stress value is safe or not, whether the particular stress whatever you are getting sigma 1 or sigma 2 is under the safe condition or not. So for that we have to apply the theories of elastic failure, right? So this is so basically theories of elastic failures are categorized into three main categories: maximum principal stress theory, also called as a Rankine's theory; maximum shear stress theory, also called as a Coulomb's, Tresca and Guess theory; distortion energy theory, which is also called as a Huber, von Mises and Henke's theory. Okay, now first of all let us understand the maximum principal stress theory. What does this theory has to say? Okay, now already I have created a background. Now let us understand what do you mean by the maximum principal stress theory. Okay, now it states that whenever a body is subjected to a combined loading, the combined loading, that is, it may be a combination of normal and shear stresses, or it may be a combination of biaxial and triaxial stresses, then in such case the failure occurs when on some point the value of maximum principal stresses will be equal to the maximum value of a stress at a point during uniaxial tensile test. Means what I have to say? So let us say that sigma x is equal to allowable stress or the maximum stress which is obtained from the simple test of tension, right? So this is the maximum value, and let us say that sigma 1 is greater than sigma 2 greater than sigma 3. So sigma 1 is the maximum principal stress. So theory says that sigma 1 is equal to sigma max, that is sigma max is equal to SYT. So sigma 1 is equal to SYT for tensile and sigma 1 is equal to SYC for compressive. This is what the maximum principal stress theory has to say. That is, a maximum principal stress is equal to the maximum value of a stress obtained from the uniaxial tensile state, that is a SYT in case of the tensile, or SUT in case of the brittle material, or SYC compressive, or SUC in case of the brittle material. So depending upon the material is ductile or brittle, you can take sigma 1 is equal to SYT or sigma 1 is equal to SUT. So basically the sigma x is nothing but a allowable stress which is equal to sigma m, and normally we consider the factor of safety. So I have written here sigma 1 is nothing but a SYT upon f of s for tensile, and sigma 1 is equal to SYC upon f of s for compressive. So I hope you have understand the statement and what does this theory has to say. Okay, now let us go into some deeper insights. Now basically in the last video I have explained how to calculate the sigma 1, sigma 2, which are nothing but the major and minor principal stresses. So we get a formula in such a manner: sigma 1 is equal to sigma x plus sigma y upon 2 plus under square root of so and so, and sigma 2, that is a minor principal, sigma x plus sigma y upon 2 minus so and so. Okay, so already we have, from the Morse circle we can calculate the value of sigma 1 and sigma 2. Okay, and now as I earlier said that now let us say that there can be 4 cases basically for the values of sigma 1 and sigma 2. Like there can be a like stresses or there can be a unlike stresses. Okay, so what are the 4 cases? So case number 1 can be the sigma 1 is greater than sigma 2, right? And sigma 1 is a tensile load, it's a tensile stress, you can say. Second case can be sigma 2 is greater than sigma 1, where sigma 2 is nothing but a tensile stress. Third case can be sigma 1 is greater than sigma 2, where sigma 1 will be compressive. And fourth case you can consider is that sigma 2 is greater than sigma 1, where sigma 2 is nothing but a compressive. So once we take sigma 1 greater than sigma 2, once we take sigma 2 greater than sigma 1, once we take sigma 1 tensile, once we take sigma 2 tensile, once we take sigma 1 compressive, once we take sigma 2 compressive. So tensile will be negative, positive, and compressive will be negative. Then normally we are assuming that SYT is equal to SYC. If yield strength in tensile loading is, let us say, 200 megapascal, so compressive strength in tensile for a ductile material SYC or a brittle material SUC is 200. So we are considering it as a equal, we are assuming it as a equal. Okay, so let us see what happens. Now basically what is a safe condition? Now what does the theory says? Theory says that the sigma 1 should be equal to the SYT, right? Now SYT is nothing but the value, or you can say the maximum stress, which is obtained from the tensile simple tension test. We are comparing with the principal stresses, which is obtained from the combined loading condition, right? So we are comparing the combined loading practical case to the experimental results of a simple tension test, and then we are forming a region, and then we will comment whether what is the safe region and when will be the corresponding component will be safe in that particular region, right? So basically for the case number 1, what we can say that the sigma 1 should be less than equal to plus SYT. It's a tensile, right? So when sigma 1 is less than equal to plus SYT, so whenever you will compare this principal stress, let us say sigma 1 is the major principal stress, or you can say the maximum principal stress, then this maximum principal stress is less than equal to the SYT, that is yield strength obtained from the tension test experimentally, is less, you can say, then you can say that it is a corresponding design is safe. Similarly, if sigma 2, if you consider sigma 2, then sigma 2 is less than equal to SYT, plus SYT. Okay, then the third case, sigma, we consider the compressive case, so sigma 1 is less than equal to minus SYC, and fourth case is sigma 2 is less than equal to minus SYC. Okay, now since we are considering a limiting condition, means what, the sigma 1 should be either less than equal to plus SYT or minus SYC. So sigma 1 is equal to plus SYT or sigma 1 is equal to minus SYC will be the limiting condition, right? So we will be to draw the region of safety, we will be considering sigma 1 is equal to plus SYT minus SYT, sigma 2 is equal to plus SYT minus SYC, right? So we are considering a limiting condition. So this is the safe condition, right? I hope you are understanding this. So you can see that if let us plot a vertical axis and a horizontal axis. On horizontal axis, let us take a sigma 1 principal stress, and on y axis you take a principal stress sigma 2. Okay, now on this sigma 1 axis, okay, mark a point sigma 1 is equal to plus SYT. Since it's a tensile, it will be positive, come towards the right hand side. So mark a point and draw a, now you know that if the equation is, let us say, x is equal to 10, okay, so the line will be parallel to y axis on the right hand side. If the equation is x is equal to minus 10, so line will be parallel to y axis and to the left hand side. Similarly, if y is equal to 10 plus minus 10, then the line will be parallel to x axis. So similarly, let us say that the sigma 1 is on the x axis, so sigma 1 is nothing but a plus SYT. So SYT will be some constant value, maybe 100, 200, 400 megapascal something. So that constant value, whatever will be the constant value, you plot over here, and draw a line AB bar parallel to this y axis or sigma 2 axis. Now similarly sigma 2 is equal to plus SYT. So sigma 2 is equal to plus SYT. So obviously now sigma 2 is on the y axis, so you have to draw a line parallel to the x axis. So you will get a line BC, which gives you the sigma 2 is equal to plus SYT. Now similarly sigma 1 is equal to minus SYC. Okay, so minus SYC will come to this side. So mark a point, whatever will be the value of minus SYC, minus 100, minus 200. You mark a point and draw a line parallel to the y axis and mark it as a CD. Similarly for sigma 2 is equal to minus SYC, plot this point sigma 2 is equal to minus SYC accordingly, and draw a line parallel to this x axis, and you will get a line AD. So in this way you will get a complete region which is shown by the hatching lines, area ABCD. Now this area ABCD is a complete region which is called the region of safety, and since we have considered SYT is equal to SYC, we are getting a square. I hope you have considered this. I hope you have understand this. So this is how we draw the region of safety. And now let us say that according to the maximum principal stress theory of failure, okay, if any point which is having a coordinates or having a principal stresses sigma 1 and sigma 2, if they falls outside the square, then it indicates a failure condition. And on the other hand, if a point having coordinates sigma 1 sigma 2, that is the principal stresses, falls inside the square, the design is safe and the failure may not occur. This is the outline, you can say this is the concept of maximum principal stress theory. Now basically if you want to understand more, let me take one example. Now let us say that I am taking you consider any machine part, okay, any part which is fitted into the machine. Now in the practical case, let us assume that this machine part is subjected to a combined loading in x as well as y direction, right? So now basically what will you do? You will by using a principal stress and the Mohr circle concept, you will find out the values of sigma 1 and sigma 2. You have got the values of sigma 1 and sigma 2. Now you of a same material will take a specimen and you will conduct a simple tension test subjected to uniaxial tensile load. Okay. Now you will get some mechanical properties like SYT or SUT, ultimate tensile strain, percentage elongation, yield strain. Okay. Now let us say you are getting a SYT value. Okay. Now what we will do? You will compare this sigma 1 with SYT, and if this sigma 1, so what will happen? If this sigma 1 is less than the plus SYT, the condition is safe. You can say it is your particular specimen is or material is safe. If the value of sigma 2 is less than plus SYT, it is safe. If value of sigma 1 is less than minus SYC, then you can say the specimen or the material is safe. If value of sigma 2 is less than minus SYC, you can say that the material is safe. Okay. So in this way what we do the comparison. So basically this theories of elastic failure provides a relationship between the strength of a machine component subjected to the complex state of stresses with the mechanical properties obtained in the tension test. So with the help of these theories, the data obtained in the tension test can be used to determine the dimensions of the component, whatever may be the nature of stresses which are induced in the component due to the complex loads. So I hope now it is clear for you how does this theories of failure works. Okay. So basically I have already explained you these basic concepts and the theories of failure. Now let us understand the next theory of failure, that is a maximum shear stress theory. Right. Now what does this maximum shear stress theory has to say? Now earlier theory, which was also called as a maximum principal stress theory, okay, this maximum principal stress theory has considered the maximum and the minimum principal stresses, it is sigma 1 and sigma 2, right? So now basically again in the Mohr circle, again you are also getting a maximum shear stress tau max. Okay. Now let us say what does this theory says, that is a maximum shear stress theory. Okay. Now this theory states that when a component is subjected to complex loading, whenever a component is subjected to complex loading, it's a combination of loads, shear and normal stresses, or biaxial or triaxial stresses, whatever it may be, that particular mechanical component will fail when the maximum shear stress at a point in the component, will be equal to the maximum shear stress at a point in a specimen in a uniaxial tensile test when yielding starts, right? So thus the maximum shear stress, okay, maximum shear stress of a component which is subjected to a complex loading will be equal to the maximum shear stress you are obtaining from the uniaxial tensile stress. Okay, so when these two values will be equal, you can say that this theory will, this your component will fail. So this is the statement of this theory, right? Now let us for example let us consider a simple tension stress where the specimen is subjected to the uniaxial stress, right? So since the specimen is subjected to the uniaxial tensile stress, okay, so that is only in one direction, okay. So if it is subjected only into the one direction, so you will get only one principal stress, that is a sigma 1. In biaxial you will get sigma 1, sigma 2. In triaxial you will get sigma 1, sigma 2, sigma 3. Now in uniaxial tensile stress you are getting sigma 1 only, okay. So if you consider the Mohr circle for stresses, you can see that you are getting a sigma 1, which is a maximum principal stress, and sigma 2 will be obviously 0. Now again I am not saying that sigma 2 is not present. Oh, it is present, sigma 3 is also present, but their magnitudes are 0. That is only the case. So in this case, in uniaxial tensile loading condition, sigma 1 is having some specific value and sigma 2 will be equal to the 0. And again you will also get a value of tau max, which is nothing but a maximum shear stress, okay. Now already I have explained specimen is subjected to the uniaxial stresses sigma 1, sigma 2 is equal to 0. So now from this Mohr circle you will get a value of tau max, obviously. So when sigma 2 is equal to 0 and there is a uniaxial condition, loading condition, this tau max will be exactly equal to the half of this sigma 1, that is a maximum principal stress. So tau max will be equal to sigma 1 upon 2. Okay, this Mohr circle I have already explained. I am repeating again. You watch the last videos where you will understand how to graphically plot this Mohr circle. So tau max is equal to sigma 1 upon 2. But already we have now studied the maximum principal stress theory, and there we have understand that when the maximum principal stress sigma 1 is equal to the SYT, your component will fail, right? Means what, your sigma 1 should be less than SYT, okay. So when sigma 1 is equal to SYT, okay, so what will be the tau max? Putting sigma 1 here, you will get tau max is equal to SYT upon 2. So maximum shear stress is nothing but the half of the SYT, that is a shear, that is nothing but the SYT is nothing but a yield strength or yield strength in tension. SYT is nothing but a yield strength in the tension. So what does this theory has to say? This theory, therefore tau max is equal to SYT upon 2 means what? The maximum shear stress theory predicts that the yield strength in shear, yield strength in shear will be half of the yield strength in tension. Means what? SSY is nothing but the yield strength in shear. Shear madhe, in shear what will be the yield strength? That will be equal to half of the SYT, that is SSY is equal to 0.5 times SYT. This is what this theory has to say. So again, for the maximum shear stress theory, again you can consider a sigma 1, sigma 2 and sigma 3, the three principal stresses acting at some point on the component, and then you can calculate the shear stresses on three different places like tau 1 2, tau 2 3, tau 3 1, and then you can find out the largest of the stresses, and you can also what I mean to say, plot the region of safety for this, okay, in the similar manner. So I hope now you have understand the maximum shear stress theory as well as the minimum shear stress theory. Now basically one more point I would like to add is that experimental investigation suggests that the maximum principal stress theory means what? The first one, the maximum shear stress theory gives good predictions for the brittle materials, but however it is not recommended for the ductile materials. So for brittle materials this theory is more suitable as compared to the ductile material, right? This is what the experimental investigation suggests, right? And as far as this maximum shear stress theory of failure is concerned, it is widely used by designers for predicting the failure of a components which are made up of a ductile materials like transmission shaft. So for ductile material, maximum shear stress theory is more suitable, and for brittle material, maximum principal stress theory is more suitable. Okay, I hope you have understand this concept of theories of failure. Thank you so much.